Hey everybody, welcome back to Trigonometry. Today we're in section 7.1 and we're going to be talking about the law of sines. So in this section we will derive the law of sines and see where it came from. We will also use the law of sines to find the length of an unknown side of an oblique triangle. And we will also talk about a few congruence axioms that we're going to need to think about before we learn the law of cosines in the next section. Here we go. So first of all, what do we mean by an oblique triangle? Well, an oblique triangle is just a triangle that is not a right triangle. Now, in chapter 2, we talked about how to solve right triangles using the Pythagorean theorem, but we also know that the Pythagorean theorem does not work on oblique triangles. It only works on right triangles. So if we're going to solve oblique triangles, we're going to need two other laws to help us do that, and the first one is the law of sines. Now, rather than just writing the law of sines on the screen, I thought it would be a good idea for us to start with an oblique triangle and develop the law of sines ourselves so you'll know where it came from. Now, what I'm about to do, you can do using an acute triangle, or you can do it just as well using an obtuse triangle. It works the same in both cases, but for our purposes, I will be focusing on the acute triangle. Notice in our triangle here, we have the three angles labeled with capital letters. We have angle A, angle B, angle C. And opposite to each angle, we have the side labeled with the same lowercase letter. Now, when we were working with right triangles, angle C was always the right angle, and therefore side C was always the longest side, and we called it the hypotenuse. That no longer holds here. So any angle can have any label, but the side opposite to that angle will still be labeled with the same lowercase letter. So opposite angle A, I have side A, and opposite angle C, I have side C. We also have here an imaginary vertical line that is drawn from the top angle down to the bottom side, and this imaginary line is perpendicular to the bottom side, and that's important because that way we have two smaller right triangles formed within our oblique triangle. Now, what I want us to do is write an expression for the sine of angle A. So you can see here, if this is a right triangle, the sine of angle A would be opposite over hypotenuse. So the sine of angle A would be H over C. Okay, now let's come over here to angle C and do the same thing. We're going to write an equation for the sine of angle C. And again, sine is opposite over hypotenuse. So the sine of angle C is H over A. Now notice that both of our equations contain H. So the next thing we'll do is isolate the H in each equation. So to isolate the H here, I'm going to multiply both sides by C. The C's on the right side will divide out, and we will have H equals C times the sine of A. For the other equation, I'm going to multiply both sides by A, and the A's will divide out, and we'll have H equals A times the sine of C. So now we have H equals side C times the sine of angle A, and we also have H equals side A times the sine of angle C. But if both of these things are equal to H, then they must be equal to each other. So now we can write C times the sine of A equals A times the sine of C. And this essentially is the law of sines, but you never see it written this way. Instead, it's always solved to be in a more convenient form. So to get to that more convenient form, I'm going to divide both sides by the sine of A, and that means the sine of A will divide out from the left side. And then I'm going to divide both sides by sine of C, and the sine of C will divide out from the right side. That leaves us with side A over the sine of angle A equals side C over the sine of angle C. And this is the form that we usually see the law of sines written in. And you might be saying, well, what about angle B? What if I need to use the law of sines to find angle B or side B? Well, notice that we could rotate this triangle so that side A sits flat on the bottom, and that would put angle A at the top. And then we could use a similar process to get an expression involving side B and the sine of angle B. If we did that, then we would have something like this. In any triangle ABC with sides A, B, and C, side A over the sine of angle A equals side B over the sine of angle B. Side A over the sine of angle A equals side C over the sine of angle C. And also side B over the sine of angle B equals side C over the sine of angle C. This is the full law of sines, but this is an awkward way to write it. So usually we see it written in a more compact form, where we just have A over the sine of angle A equals B over the sine of angle B, and that's also equal to C over the sine of angle C. And since we only need to use two ratios at a time, we can use any two ratios that we want as long as we have enough information to leave only one unknown value. And whatever the other ratio is that we're not using, we just ignore it. Another way to write the law of sines is with the signs in the top. So you could have the reciprocal of each ratio, and that would be sine of angle A over side A equals sine of angle B over side B, and also equals sine of angle C over side C. This version is more convenient if you're using the law of sines to find an unknown angle, which we will do in section 7.3. But if you're trying to find sides, then you want to use the version where the sides are in the top. Let's get a couple of examples, and most students actually love the law of sines because it's so easy to use. So here in example 1, it says solve triangle ABC if angle A is 32.0 degrees, angle C is 81.8 degrees, and side A is 42.9 centimeters. Now, you do need to draw yourself a triangle, but it does not have to be to scale. So any triangle you draw will be fine, but it is helpful to have something to look at. So I'm going to just draw myself a triangle here, and I'm betting on angle A being the smallest angle. So I'm going to label this smallest angle A. And then I think I will label this angle as C. That means this other angle must be angle B. Now for the sides, the side opposite angle A is side A, the side opposite angle B is side B, and the side opposite angle C is side C. Now let's label our known values. We know that angle A is 32 degrees, and we know that angle C is 81.8 degrees, and we also know that side A is 42.9 centimeters. Now, when it says solve the triangle, you remember it means find all the unknown values. So by the time you're finished, you should have a value for every angle and a value for every side. The easiest unknown value to find here would be angle B, and we can do that by just subtracting the two known angles from 180, because we know that the interior angles of a triangle always add up to 180. So angle B will be 180 minus 32.0 minus 81.8 degrees, and that would give us 66.2 degrees for angle B. We'll go ahead and label angle B there. Now to find side B and side C, the only tool we have is the law of sines. Remember, we cannot use the Pythagorean theorem to find either of these sides because this is not a right triangle. But we do have the law of sines. Now, when you use the law of sines, you always have to have an angle and a side opposite where you know both values. And for us, that would be angle A and side A. So we're definitely going to use A over the sine of A. And let's say we want to find side B first. That means the other ratio we would use would be B over the sine of angle B. Now let's plug our known values into this equation. We do know that side A is 42.9 centimeters, And we do know that angle A is 32.0 degrees. So I've got 42.9 over the sine of 32.0 degrees. That's equal to side B, which is what I'm trying to find, over the sine of angle B, which we know is 66.2 degrees. We want to isolate side B here, so let's multiply both sides of the equation by sine of 66.2 degrees. That means the sine of 66.2 degrees will divide out from the right side, and then we will use our calculator to evaluate this expression, and you should come up with B equals 74.1 centimeters. Now, there are rules about significant digits and how many digits we should keep here, but my lab will always tell you how many decimal places you have to keep, and for us, it's usually going to be the same number of decimal places that were in the given values. So notice that the one side we were given has 1 decimal place, and so I kept 1 decimal place in our answer for side B. We also need to find the length of side C. So I have gone to a new slide here and I've recopied our triangle for us. And now let's figure out how to find side C. Again, we're going to start with A over the sine of angle A because those values were given in the problem. And this time the other ratio will be C over the sine of angle C. And again, let's fill in our known values. So we'll have 42.9 over the sine of 32.0 degrees equals C, which is what we're looking for, divided by the sine of angle C, which was 81.8 degrees. And just like when we were finding side B, we want to isolate the variable here, so we'll multiply both sides by the sine of 81.8 degrees. That allows the sine values to divide out from the right side, and then when you evaluate on your calculator, you should get side C equals 80.1 centimeters. The only thing you really have to watch out for when you're evaluating this expression on the calculator is that first of all you want to make sure that your calculator is set in degree mode, but then you also want to make sure that after you enter your first sine expression you press the close parentheses, because that won't be written necessarily, but you do need to remember to do it so that the calculator understands that you just want the sine of 81.8 and that's the end of that angle. Okay, so now we have a value for all 3 sides and we have a value for all 3 angles, so our solving is done. But at this point you always want to double check that there's not an error somewhere by just verifying that the smallest angle is opposite the smallest side and the largest angle is opposite the largest side. Because if either one of those things is not true, you do have a mistake somewhere. Now let's look at example 2. So it says Kurt Daniels wishes to measure the distance across the Gasconade River. He determines that angle C is 112.90 degrees, angle A is 31.10 degrees, and side B is 347.6 feet. Find the distance A across the river. Well, if you notice, right now we don't have enough information to set up the law of sines, because as we saw before, we would need to start with an angle and side opposite where we know both values, and right now we don't have that. But we do have enough information to find angle B, so that's what we need to do first. Angle B would be 180 minus the other 2 known angles. So minus 112.90 minus 31.10, and that gives us a value for angle B of 36.00 degrees. I'm just going to label that here on our diagram. And now you see that we have enough information to use the law of sines, because now we have angle B and side B, and we want to find side A, and we know a value for angle A. So now I can set up my law of sines as B over the sine of B equals A over the sine of angle A, and let's fill in our known values. Side B is 347.6, and that's divided by sine of angle B, which is sine of 36 degrees, and then that equals side A, which is what we're looking for, divided by sine of angle A, which is sine of 31.10 degrees. Now to isolate A, we multiply both sides by the sine of 31.10 degrees. The sine values cancel out from the right side, and when you evaluate this on your calculator, you should get A equals 305.5 feet. Now let's talk about some axioms for congruent triangles. So I want you to think about this question. How do we know that the values that we're finding using the law of sines are the only possible correct values for these problems? Well, the good news is that we know because of the congruence axioms that you probably learned in high school geometry, but you probably haven't thought about them in a while, so let's look at them together. Let's start with the angle-side-angle congruence axiom. So think about a triangle where we know two of the angles and the side that's between them. It would look something like this. So in this diagram, we know two of the angles and we have a value for the side between those two angles. This situation is called ASA, or angle-side-angle, and you can see why. ASA. So the ASA congruence axiom says that if two triangles have two pairs of congruent angles and the sides between those congruent angles are also congruent, then those two triangles are congruent. Now, we will never be working with two triangles at a time, so another way to think of this idea is to say it like this. If two angles and the side between them are known, that determines a unique triangle. In other words, there's only one way to make a triangle with this information. And that's how we know that if we had a triangle like this and we find a value for side A and we find a value for side B, the two values that we find will be the only two possible values for those sides. And here's another situation that's very similar to ASA. So if we know two angles and the side not between them, this is not ASA, this is AAS, but we can easily turn this into ASA because we can always find that third angle, right? So AAS is easily converted into ASA, so these two situations are really the same. And so that allows us to say that if two angles and any side are known, that determines a unique triangle. Now, you had no reason to realize it at the time, but just so you know, example 1 was an AAS situation. Here is our triangle from example 1. Notice that we have angle, angle, and a side not between them. So that's AAS. And example 2 was an ASA situation, which you can see here on the diagram, ASA, where we knew two angles and the side between them. And since we've already worked both of these examples, we know that ASA and AAS triangles can both be solved using the law of sines alone, and we don't need any other fancy formulas to help us do that. So here are your steps for solving ASA and AAS cases. First, subtract the two known angles from 180 degrees to get the third angle, and then use the law of sines with the sides on top to find the length of each unknown side. And that's it, you're done. The law of sines is very easy to use on ASA and AAS triangles. Now let's think about the side-angle-side congruence axiom. So when we know two sides of an oblique triangle and the angle between those two sides, that's called SAS, and you can see why. So the SAS congruence axiom says that if two triangles have two pairs of congruent sides and the angles between them are also congruent, then those two triangles are congruent. And that means that if two sides and the angle between them are known, that's enough information to determine a unique triangle. If you know these two sides and you know this angle and those values are fixed, they can't change, then there's only one way to form a triangle with that information. But notice that we don't have enough information here to set up the law of sines, so we will need some extra help solving SAS triangles. And let's look at the side-side-side congruence axiom. So this situation is called SSS. Notice that we have a value for each side, but no values for any of the angles. But we do have an SSS congruence axiom, which says that if two triangles have three pairs of congruent sides, then those two triangles are congruent. In other words, if three sides of a triangle are known, that determines a unique triangle. And so there's only one possible value for each angle. And you can definitely tell here that there's not enough information to use the law of sines because we don't have any information about any of the angles. So this is another situation where we will need another formula to help us. And for SAS and SSS, we're going to need the law of cosines and the law of sines. So that's why in the next section we will be learning about the law of cosines. Now there's one more situation that we're just going to touch on because I want you to know that it exists, but we're not going to be solving any triangles of this type. The last situation is side-side angle. So the situation where two sides and one angle not between them are known is called side-side angle. There is no congruence axiom for the SSA situation because SSA can produce either no triangle, one triangle, or even two different triangles depending on the measure of the known angle and the length of the known sides. So take a look at this situation. Here we have SSA. In other words, we have a known side, another known side, and then the angle that's not between them. The problem is this information does not form a triangle because no matter what angle we make with this side right here, this little side is not long enough to meet the third side of the triangle. So without changing one of these values, we're not going to get a triangle. This is an example where side-side angle formed no triangle. And here's an example where side-side angle formed two different triangles. Notice here we have side A equal to 22.8, side B equal to 24.9, and angle A is known to be 55.3. So side-side angle formed an acute triangle here, but that same information forms an obtuse triangle if we just swing side B over this way. So you see that we got two different triangles here using the same side-side angle information. So you can see that the SSA situation can be a little tricky. Let's sum up. So the bottom line is that the SSA situation does not guarantee a unique triangle, so more analysis would be needed before attempting to solve a triangle based on SSA information. In this course, we will not work with any triangles in the SSA situation, but I did want you to know that they exist. And more importantly, we found out in this section that we can solve ASA and AAS triangles using only the law of sines. And we learned how to identify SAS and SSS cases, but we know that we can't use the law of sines alone to solve them because we don't have enough information. And so in section 7.3, we'll learn how to use the law of cosines, and then we will use the law of cosines and the law of sines together to solve these two cases. Okay, you guys, so that's all we've got for section 7.1. I'll see you next time in section 7.3 where we will finish out our course. Bye-bye now.